A very good evening, a good afternoon, and good morning to all. I, Dr. Pallavi Saxena, iLEAPS SSC member, and Dr. Samina, iLEAPS IPO, welcomes you all on the occasion of our seventh talk in the iLEAPS Global Colloquium Series 2023. So with an awesome response received from all the attendees and the participants of iLEAPS Global Colloquium Series in 2022, so we have decided to continue in 2023 also. So let me talk some brief about iLEAPS. So iLEAPS is Integrated Land and Atmosphere Interactions, which is a global research project of Future Earth. iLEAPS provides understanding of how interacting physical, chemical, and biological processes transport and transform energy and matter through the land-atmosphere interface. The prime purpose of this colloquium is to introduce the scientific community with the distinguished and significant work of eminent scientists all over the world. It is basically a bright opportunity, particularly for the early career researchers, to establish the bridge between the ideas and the knowledge through this platform. So our today's speaker is Dr. Owen R. Cooper, who is Senior Research Scientist at Ceres, University of Colorado, Boulder, US, and at NOAA Chemical Sciences Laboratory at US. So he received his PhD from the Department of Environmental Sciences at the University of Virginia in 2001, and he currently serves as a CIRAS Senior Research Scientist at the University of Colorado Boulder. He works closely with the government scientists in NOAA's Chemical Sciences Laboratory in Boulder, Colorado, with the goal of conducting scientific research that is highly relevant to public health issues and policy development. Owen's interests pertain to regional and intercontinental transport of atmospheric trace gases, dust, and aerosols, trends in US and global air quality, the global tropospheric ozone budget and trends, and the stratosphere-troposphere exchange processes. Owen is an author on 123 peer-reviewed publications and has contributed to several assessment reports, including the 5th and 6th IPCC assessment reports, the annual State of the Climate reports, and the Task Force on Hemispheric Transport of Air Pollution. In 2014, he established IGAC's Tropospheric Ozone Assessment Report, TOR, and has continuously served in TOR leadership roles. So today he will be talking about the ever-changing global tropospheric ozone trends. And in this, he will discuss that about the overview of the IPCC AR6 assessment and tropospheric ozone's global distribution and trends and the key drivers. So I again welcome Dr. Cooper. So Dr. Cooper, it's over to you.
Great. Thank you very much, Pallavi and Samina, for inviting me. It's a pleasure to speak to the iLEAPS community. I'm just going to see if I can share my screen here. And just give me a thumbs up, Pallavi, when you can see it.
Yeah.
We're good?
Perfect.
Okay, great. All right. Well, again, thanks very much for having me. As Pallavi said, my presentation today is an update on ever-changing global tropospheric ozone trends. I got a lot to cover in just about 40 minutes, but I think I can do it. I have 8 topics here. We'll start off talking about why tropospheric ozone is important, and then I'll review the IPCC assessment of ozone trends. We'll then move into the emissions that control ozone production, and I'll discuss the observational evidence for global scale ozone increases. And then in contrast, we'll talk about the very variable ozone trends at the surface. We'll also talk about some exciting new research involving the impact of the COVID-19 economic downturn on ozone distribution and trends. We'll look into a possible future scenario, And I'll finish just by giving everyone an update on the tropospheric ozone assessment report. So let's just get the basics out of the way. I think most of us probably know that ozone is 3 oxygen molecules bonded together. We also refer to it as O3. And it plays a very important role in protecting life on Earth. In the stratosphere, we have a very, very thick layer of ozone that filters out ultraviolet radiation. But I won't be focusing on the stratosphere today. I'll be focusing on the troposphere. So here on the right, we have a nice diagram here. It's from the latest stratospheric ozone assessment report from WMO. And it shows the vertical distribution of ozone in the atmosphere from the surface up to about 35 kilometers. And you can see very clearly at around 20 to 25 kilometers, the large amount of ozone that's in the stratospheric ozone layer. And that's about 90% of the full column of ozone from the surface to the top of the atmosphere. And then down in the troposphere, below 15 kilometers, we have about 10% of the column of ozone in the atmosphere. So ozone is a short-lived trace gas. It's also known as a short-lived climate forcer. It originates naturally in the stratosphere, but in the troposphere, it's produced by photochemical reactions involving sunlight and precursor gases. And these precursor gases are nitrogen oxides, non-methane volatile organic compounds, methane, or carbon monoxide. And they have many natural sources, including wildfires, biogenic hydrocarbon emissions, lightning, and biogenic nitrogen oxide emissions from soils. And importantly, there's also a very strong anthropogenic contribution to these precursor gases, mainly from fossil fuel and biofuel combustion and from crop burning. So why is ozone important? Well, just basically, it is the primary source of the hydroxyl radical, which is often referred to as the detergent of the atmosphere because it breaks down most of the compounds that are emitted into the atmosphere. It's also the third most important greenhouse gas after CO2 and methane. And then in terms of human health, it's an air pollutant that impairs human lung function. And it also impacts ecosystem productivity and crop yields. According to Global Burden of Diseases 2019 study, they estimated there are 365,000, plus or minus 50%, premature deaths worldwide in the year 2019 due to ambient or outdoor ozone pollution. And that's an increase of 16% from the year 2010. And most of these deaths occur in India and China. And now India actually surpasses China in projected ozone deaths. And that's shown here on the right. This is data from the Global Burden of Disease study showing premature deaths per year from 1990 through 2019. So the dark blue line at the top is for the entire world. And then we have it broken down into 4 regions. We have China in light blue, India in green, the United States in orange, and the rest of the world in yellow. So things have gotten better in China over the past 10 years, but ozone air pollution in India is worsening. And then in terms of crop yields, ozone damages vegetation, and it's known to reduce crop yields worldwide. So for example, for wheat, we see on average a 7 to 12% reduction in crop yield. And these reductions are 6 to 16% for soybean, 3 to 4% for rice, and 3 to 5% for maize. And the greatest impacts are again in India and China. So our evolving understanding of global ozone observations and trends is documented every few years by the assessments of the Intergovernmental Panel on Climate Change. And these well-known reports began in 1990, and they're updated about every 5, 6, or 7 years. And we've now seen the release of the 6th assessment report, which came out in 2021. And I'm going to share the results from this assessment report regarding tropospheric ozone. So here are the key findings. Based on model calculations and also supported by observations, IPCC has assessed there's about 347 teragrams of ozone in the troposphere. That's for the year 2010. and it has an effective radiative forcing of about 0.47 watts per meter squared, plus or minus 50%. And that's from 1750 to the present day. And this includes both tropospheric and stratospheric ozone. And this is about 17% of the total effective radiative forcing from all greenhouse gases combined. IPCC also determined, based on models, that the tropospheric ozone burden increased by about 45% from 1850 to the present day. And this is continuing. And that's summarized here in this nice figure from Chapter 6 of IPCC. And this shows the model estimated evolution of the tropospheric ozone burden from 1850 to the present day in blue, and then with a future projection for the 21st century in red. And you can see how the increase throughout the 20th century has been more or less steady, and we're expecting the increase to continue throughout the 21st century. And most of this increase, and I'll talk about this later, a lot of this will be influenced heavily by methane concentrations. And IPCC also pointed out that trends at the surface don't necessarily match the trends in the free troposphere. And we'll talk about that in a few slides. So how has IPCC's assessment of ozone changed over the years? Well, in terms of climate change, the important number is its radiative forcing. And in 1990, in the first assessment, they didn't give a quantification of ozone's radiative forcing. That didn't happen until the second assessment in 1995. And there they estimated that the radiative forcing would be about 0.4 watts per meter squared, plus or minus 50%. And then in the third assessment, that number was revised downwards slightly to 0.35 watts per square meter. It stayed roughly the same for the fourth assessment, which won the Nobel Peace Prize. And then in 2013, it was increased back up to 0.4 watts per square meter due to the ongoing increases of ozone in the troposphere. And then for the most recent assessment, it's now increased slightly to 0.47 watts per square meter, again reflecting the continuing increase in the atmosphere. So let's talk now about the emissions that control global ozone concentrations. This is a nice update on CO2 emissions from the Global Carbon Budget 2022 report. These come out every year in Earth System Science data. Now, CO2 is not an ozone precursor, but it is a good indication of the amount of fossil fuels that are being burned worldwide. So from 1960 to the year 2022, CO2 emissions increased by about a factor of 4. And that roughly corresponds to the increases in all the other ozone precursors, but not exactly. And then over here in the top right, we see CO2 emissions by region. So in the early 2000s, the United States was the major emitter of CO2 emissions, but they've come down slightly as industry has declined in the US. And that's been compensated by the increasing industry and economy of China, which is now by far the largest emitter of CO2 emissions. And we also see that India is increasing as well since the year 2000. Here's the latest observations on the left of the global methane concentration. This is from the NOAA Global Observational Network. And we can see very clearly that in the remote free troposphere, we're seeing an increase of methane from the early 1980s to the present day. And then this figure was updated in July of this year. So this is very, very current data. And we can see that in the early 2000s, there was a brief leveling off of methane. And people thought, well, perhaps we're done with methane increases. But that's not the case. Since 2005, methane has once again begun to increase quickly. And the global concentration has gone up by 8% since 2005. And methane is ubiquitous in the troposphere. And wherever you have methane, if you also have NOx emissions, you'll produce ozone. And with increasing methane, we're expecting the global tropospheric ozone burden to also increase. One of the other very important ozone precursors is nitrogen oxides, which are produced by fossil fuel combustion and also from wildfire burning and crop burning. And we can see from 1950 until the present day, we've seen an increase of nitrogen oxide emissions globally. And this is this, I should point out, this is the CMIP6 emissions inventory that was used by the most recent IPCC assessment. So the black dots here are the global emissions. Red is northern hemisphere mid and high latitudes, and you can see they peaked in the early 1990s and have decreased slightly. But that decrease in nitrogen oxide emissions at northern mid and high latitudes has been more than compensated by increases in the tropics, especially in the northern tropics. So that's what's driving the increase of ozone in the atmosphere. It's the increase of all those precursors. But what's the observational evidence? Because as I pointed out, our estimates of ozone increases since the 17 and 1800s is based on models. Well, we don't have much in the way of observations from the 1750s through the end of the 19th century. The observations that are available are very unreliable. So in terms of accurate observations, we don't have anything reliable from the 19th century. But as we move into the 20th century, from about 1900 to the early 1970s, we're beginning to find a wide range of observations worldwide, but based on fairly uncertain wet chemical methods. And then the modern era for ozone observations begins about 1970 with the advent of ultraviolet absorption instruments that became commercially available. And now we do have a lot of networks worldwide to estimate ozone trends and the ozone burden. So based on observations, we do see an increase of ozone from the mid 20th century to the present day. And I'll show that here in this slide. This is an excellent figure from a paper that came out of the Tropospheric Ozone Assessment Report that was led by David Tarasik and Ian Galbally. It came out in 2019. And this shows everything we know about ozone observations at rural locations in the 20th century. So you can see from 1900 until the late 1970s, we don't have a lot of data, but we do have sort of consistent observations at rural sites at northern mid-latitudes that show that throughout much of the 20th century, especially in the mid-20th century, sort of the average rural background ozone levels were about 25 parts per billion. And that's what we call the historical data. And then for the present day, from 1990 to 2014, when we look at ozone observations from modern UV absorption instruments in the same regions, we see an increase somewhere in the range of 30 to 70%. And that generally compares well with what the models are telling us. Here's a nice summary figure from IPCC AR6. This is from chapter 2. And this shows long-term ozone trends from the mid-1990s to the present day. And this figure shows ozone trends in the lower troposphere on the left, in the mid and upper troposphere in the center, and for the full tropospheric column on the right. And these trends are based on observations, and they're arranged by latitude on the y-axis. So they begin at 90 degrees north at the top, down to the equator, and then down to 90 degrees south. And then on the x-axis, we have the ozone trend from all these different observations in parts per billion per decade. So if we focus just on the surface and the lower troposphere from remote rural sites and from IAGOS commercial aircraft observations, we see that in the tropics, there's a consistent increase of ozone from the mid-1990s to the present day. But when we look at mid and high latitudes, we see a mixture of trends from strongly positive to strongly negative. And I should point out though that these observations are not distributed evenly. They're sort of clustered mainly in Europe and North America. So they're not globally representative. So it's difficult to understand global ozone trends from limited surface networks. But when we come into the mid and upper troposphere, we see consistent positive ozone trends from ozone sondes and IAGOS commercial aircraft from 1994 through 2016. And then when we look at the column trends from ozone sondes and from satellite products, they also, for the most part, show an increase of ozone from sort of northern mid-latitudes into the tropics down to southern mid-latitudes. So this is the observational evidence that ozone has increased or has continued to increase since the 1990s. And then we also are fortunate to have the OMI and the MLS satellite instruments on the NASA ARA satellite. They've been in orbit since 2004. This is the OMI MLS combined tropospheric column satellite product. It's produced by Jerry Zemke at NASA Goddard, and it's updated every year in the annual State of the Climate reports. And here in the map at the bottom, you can see in brown where ozone has been increasing since 2004. And there aren't really any ozone decreases, maybe some weak ones off the coast of Spain and Portugal. But for the most part, it's been a general increase since 2004. And the strongest increases are right where we would expect to find them, over South and East Asia, and then extending across the North Pacific Ocean. And then over here on the left, we have monthly mean global tropospheric ozone, and also broken down by the Northern Hemisphere and the Southern Hemisphere. And all these regions generally show a steady increase of ozone since 2004, which is probably driven a lot by the increase of methane in the atmosphere. Here's a nice paper that summarizes what's driving tropospheric ozone trends. This was led by Yuchang Zhang and Jason West at the University of North Carolina, Chapel Hill. And they used the CAM-CHEM model to look at ozone changes from 1980 to 2010. And main conclusion from this study was that a lot of the ozone increase globally is being driven by ozone production in the tropics. So here's the main summary figure from the paper. Here in the top left, the model estimates that the tropospheric ozone burden increased by about 28 teragrams from 1980 to 2010. That's about a 10% increase. And you can see most of the increases are in the tropics. Right below that figure in the bottom left, we can see that there's about an 8 teragram increase just from the general increase of NOx emissions worldwide. And then in the bottom right, we see another 7 teragrams of increase just from the methane increases worldwide. But what's most fascinating is this plot here in the top right. And this is what happens to ozone when you keep emissions at the same intensity, but you just shift them towards the tropics from northern mid-latitudes. And here we see that about half of that ozone increase globally is just due to the fact that we're moving emissions from high latitudes into the tropics, where ozone production efficiency is much greater because you have lots of sunshine year-round. So that's the overall view of the global trends. Now I want to focus on trends at the surface because they are highly variable and don't necessarily match what we see in the free troposphere. So this is what's become now a well-known figure from the Tropospheric Ozone Assessment Report. This shows the global distribution of observed ozone for the period 2010 to 2014. And we're focusing on the 98th percentile in the summertime months. So we're focusing on extreme ozone levels just to see where ozone pollution is most extreme worldwide. And from this figure, we can quickly see that the highest ozone values are found at northern mid-latitudes for the most part. And we see strong enhancements in California, Mexico City, in Southern Europe, in Israel, Northern India, and really all across East Asia. Here's the same plot, but now we're looking at a different metric. This is the number of days per year the ozone exceeds 70 parts per billion based on the maximum daily 8-hour average. And the reason we're focusing on this metric is because it's the United States ozone standard, which is based on clinical trials, which show that when you get to concentrations above 70 parts per billion, we see decreased lung function in healthy young adults. So this matches very well what we see with the 98th percentile. And you can see that in many parts of the world, we see more than 15 days per year when ozone goes above this critical level. And with this figure here, we zoom in then on North America, Western Europe, and East Asia. And now you can really see the hot spots for 2010 to 2014. And in those days, the highest number of exceedances was found in California, Phoenix, Denver, some large urban areas in the eastern US. When we get to Europe, it's mainly in southern Europe, especially in the Po Valley of northern Italy. And when we come to East Asia, we see most areas have a high number of exceedances, with the exception of a few remote islands and northern Japan. And now let's look at the trends. This is sort of the popular tour method of showing trends. These vectors indicate the ozone rate of change. For this particular metric, we're looking at the number of days per year that ozone goes above 70 parts per billion. So if a vector is horizontal, there's no change. If a vector is pointing straight up, then the number of days per year above 70 parts per billion is going up at the rate of 2 days per year. And if a vector is pointing straight down, then the number of days per year above 70 is decreasing at the rate of 2 days per year. Blues are decreases, reds and oranges are increases, and greens are basically no change. So from this figure, you can quickly see that it's good news across much of the United States. The high ozone events are coming down. We see a lot of decreases also across Europe, but in East Asia, it's a mixed bag of results. We see some decreases and also some increases. So that tour study ends in 2014, and now we're in 2023, and things keep changing. So what's the most recent update on ozone trends? Well, we're working on that with the second phase of the Tropospheric Ozone Assessment Report, and here are some preliminary results, just focusing on the United States and southern Canada. At the top here, I'm showing that same ozone metric, number of days per year the ozone goes above 70 parts per billion. But at the top here, we're focusing on the period 2000 to 2004. And then at the bottom, we're focusing on the more recent period of 2015 to 2019. Now, I could have shown also data from 2020 and 2021, but as we'll talk about in a few minutes, those years were anomalous because they were impacted by the COVID-19 pandemic. So we're just gonna look at 2015 to 2019 as an indicator of typical present day ozone values. And what you can see is really great news for air quality in the United States in terms of ozone pollution. Back in 2000 to 2004, we had many cities across the US where we had more than 15 days per year above 70 parts per billion. Today, in the eastern US, we don't have any days or any cities that have more than 15 days per year above 70 parts per billion. Now in the West, we do have some regions where these high exposures persist, like Denver, Phoenix, Las Vegas, and much of California. But clearly in the eastern United States, the air quality has greatly improved. And this is largely attributed to decreasing NOx emissions from power plants and automobiles. And to give a more detailed view on this rapid decrease of ozone in the eastern US, I'm going to show some data from a very nice rural regional monitoring site. It's called Big Meadows. It's in Shenandoah National Park, and it's on a ridgeline about 1 kilometer above sea level. And there are no appreciable local emissions. So it really does represent ozone levels, background ozone levels in the mid-Atlantic states of the eastern United States. And here I'm showing every single maximum daily 8-hour average ozone value from 1987 through the end of 2021. The gray line here is 70 parts per billion. That's the US ozone standard. So you can quickly see the years in which ozone exceeds the US ozone standard at this background site. And the dark blue numbers at the top shows the number of days per year the ozone goes above 70 parts per billion. So back in the 1980s and 1990s, it was very common to have more than 30 days per year above 70 parts per billion. And the peak was 1998 with 81 days. But ever since 1998, the number of days has come down. And by 2013, there wasn't a single day that exceeded 70 parts per billion. And in the 9 years from 2013 to 2021, there's only been one exceedance. So this really is just very clear evidence that extreme ozone events have largely disappeared from much of the eastern United States due to emission controls. Okay, I've already talked about a little bit about the impact of COVID-19, but let's look at this in much more detail. A nice paper came out in Environment International about a year ago, maybe a year and a half ago. It was led by Ranjit Soki at the University of Hertfordshire in the UK. And he has many, many co-authors here because they looked at air pollution data at dozens of monitoring sites worldwide. And this map here shows all the cities that they looked at. And they looked at all the air quality data they could find for 2020 to look at the impact of COVID-19 on air pollution. And I think most of us are familiar with the general impact. We all lived through this, this period in time where we had to experience lockdowns, and we all know about the decreased economic activity, and that led to reduced air pollution emissions. So here's an excellent figure from Ranjit's paper. It's very busy, but it does summarize nicely the changes in air pollution levels in 2020. And over here on the left axis, we have all the different cities you saw on the previous slide. Along the x-axis at the top, we have changes of PM 2.5, PM 10, nitrogen dioxide, ozone, carbon monoxide, and SO2. And then at the bottom here, we have 4 different periods, or actually 5 different periods for each pollutant. We have the pre-lockdown period in early 2020, the partial lockdowns as cities began to take action to reduce movement of people. We have the full lockdown period in the late spring, the partial relaxation period, and then the full relaxation period by late 2020. And greens and blues indicate decreases of pollutants, and oranges, reds, and pinks indicate increases. I'm just going to focus on nitrogen dioxide and ozone. Nitrogen dioxide is, of course, a major ozone precursor, and we can see that during the full lockdown period around the world, we see strong decreases of nitrogen dioxide. And that's an ozone precursor, but we don't see consistent decreases of ozone around the world. In many places, we actually see increases of ozone. And that's because these lockdowns occurred mainly in the springtime, when ozone production is fairly limited. Most ozone production occurs in summertime. And in urban areas, high levels of nitrogen oxides can actually destroy ozone. So in urban centers, when we reduced nitrogen oxide during the COVID period, we actually saw an increase of ozone. Okay, but that's not what we saw in the free troposphere, and I'll show that now. 2 very nice papers came out in 2021 that looked at ozone anomalies in the free troposphere of north and mid latitudes based on ozone sondes and IAGAS commercial aircraft. And these were led by Wolfgang Steinbrecht at DLR at Deutsche Wetterdienst in Germany. And it was also led by Kai-Lan Chang at my institute, Ceres and NOAA Chemical Sciences Laboratory. And they found fairly consistent ozone decreases at north and mid latitudes of about 5%. And here's a summary from Kai-Lan Chang's paper. This shows annual ozone anomalies in the free troposphere above Europe and Western North America from 1994 through 2020. And this is based on ozone sondes and IAGAS commercial aircraft. Down at the bottom here, you see the monthly mean ozone and the seasonal cycle. So overall, from 1994 until 2019, there was a small weak increase of ozone in the free troposphere above Europe and Western North America. But from 2019 to 2020, we see a very abrupt decrease in ozone above both regions of about 5%. And that's the sharpest decrease we've seen at both regions simultaneously since 1994. And we attribute this to the the worldwide decrease in ozone precursor emissions during the COVID-19 pandemic. We also see ozone decreases from satellites during the COVID-19 pandemic. This is an excellent paper published by Jerry Zinke at NASA last year in GRL. He looked at 3 independent tropospheric ozone products from satellites, and he found that at northern mid-latitudes in both 2020 and into 2021, he saw clear decreases of ozone of about 5 to 8%. So that matches up very well with what the in situ observations showed. Okay, so that was the impact of COVID-19. Now let's look at a possible future scenario for ozone in the 21st century. IPCC has several estimates of ozone throughout the 21st century, depending on which shared socioeconomic pathway you choose. Some of these pathways indicate decreases of ozone precursors, others indicate strong increases. Perhaps the most popular shared socioeconomic pathway for looking at the 21st century is the SSP 3-7.0. And this is essentially a business as usual scenario. Globally, the storyline is that countries are focusing on economic development and national security with continuing regional rivalry. In this storyline, there's a low international priority for addressing environmental concerns, which then leads to strong environmental degradation in some regions. Methane increases throughout the 21st century in this scenario, and NOx emissions peak by mid-century and then decline. And this is a nice summary figure here. It was an excerpt from figure 6.18 from IPCC AR6 chapter 6, and it shows the different evolutions of methane and nitrogen oxides depending on which shared socioeconomic pathway you choose from 1850 through 2100. The one that we're focusing on is SSP 3-7.0. That's the one in bright red, and that shows a strong increase of methane throughout the 21st century. And then you see the peak in nitrogen oxides by mid-century with a decrease, but this is not evenly distributed. There's some regions of the world where NOx emissions continue to increase. So how would this storyline of emissions impact ozone globally? Well, we've already sort of seen the outcome. The figure that I showed earlier, the summary figure from IPCC, has a future projection, and that is based on the SSP 3-7.0 scenario. And that indicates a continuing increase of the tropospheric ozone burden throughout the 21st century. Now that's for the full atmosphere, but we don't expect ozone at the surface to increase everywhere. And that's because this paper here by Prodromis Zanis and colleagues, and this comes out of IPCC AR6, they show what happens to surface ozone as global temperatures increase throughout the 21st century. And that's summarized here in the figure in the bottom right. As global surface temperature increases, we actually see a decrease of ozone at the surface. So for every increase of global temperature by 1 degree C, we see on average a 1 ppb decrease averaged over the whole planet. And that's just because in a warmer climate, there'll be more water vapor in the atmosphere, and water vapor shortens the lifetime of ozone in the atmosphere. And that's summarized here by this figure. This shows the changes in surface ozone due to climate change alone. And this is based on a temperature increase of 3 degrees Celsius from the late 1800s. And for this particular scenario, that 3 degrees C temperature increase occurs sometime in the period of 2055 to 2081. And so the shading indicates the change of ozone at the surface due to climate change. Blues are decreases. So we see in most parts of the world, especially over the oceans, we see a decrease of ozone due to increased water vapor. But we also see some ozone increases in reds here. And this is mainly found over South Asia and East Asia. In both of these regions, ozone precursors are forecast to continue to increase. And when you have increasing ozone precursor emissions in association with climate change, which increases heat waves, which reduces surface winds, which increases sunlight, and which increases the temperature that allows ozone to form, we see what's called a climate penalty. So looking forward into the 21st century, if emissions continue to increase in South and East Asia, there'll be an additional 20% increase of ozone at the surface due to climate change, basically due to increased heat waves. Now, this is limited to a fairly small area of the world, but as we all know, South and East Asia are home to about 1/4 of the world's population. So this is a big deal in terms of potential damage to human health and crops and ecosystems. And then moving forward, we should also keep our eye on the impact of aircraft emissions. Now, aircraft emissions have increased globally ever since the 1960s. This is a nice figure from David Lee's recent summary of aircraft emissions. On the top here, you can see an increase of aircraft emissions. This is CO2, but it correlates with the ozone precursors. We see a strong increase from 1960 through 2018. And there's been a doubling of aircraft emissions between 1990 and 2018. And a recent paper came out by some colleagues in China who used Harvard's geochem model. And they looked at ozone increases globally from 1995 through 2017. And of the modeled increase that their model predicts for this time period, they attribute 2/3 of that global ozone increase to the increase of aircraft emissions. And the reason for this is because even though aircraft emissions are a small percentage globally of total emissions, these aircraft emissions are mainly injected directly into the free troposphere. So when you have fresh NOx emitted directly into the free troposphere, and you have plenty of methane, and if a lot of this increase is occurring in the tropics where you have lots of sunlight, then you can increase global ozone. And then looking forward, we should expect aircraft to have an even greater impact in the 21st century. Here's a couple of news headlines that came out a month or two ago showing that India is now making some of the largest new aircraft purchases in history from both Airbus and Boeing. So India will have an expanding aircraft fleet commercially over the next 10 to 20 years. And all these aircraft will be flying mainly in the tropics. And here at the lower left, I have a projection from Airbus Industries of the number of aircraft that will be in service from 2020 to 2042. So beginning in 2020, there's about 23,000 commercial aircraft worldwide. They expect that number to double by 2042. So we can expect a large increase in aircraft emissions over the next 20 years, which should then add to the increasing tropospheric ozone burden. Okay, in my last few minutes then, I'm going to talk about the Tropospheric Ozone Assessment Report, which has really helped to increase our understanding of global ozone trends. So the first phase of the Tropospheric Ozone Assessment Report, or TOR, as we call it, occurred from 2014 to 2019. And TOR is an official activity of IGAC, the International Global Atmospheric Chemistry Project. And our mission was to provide the research community with an up-to-date scientific assessment of tropospheric ozone's global distribution and trends from the surface all the way to the tropopause. And we had two deliverables. Number one was the actual assessment report itself. And number two, we built the world's largest database of ozone exposure metrics at thousands of measurement sites worldwide. And the main outcome of TOR then, of course, was the actual assessment. And that was a series of 10 papers published in the open access journal Elementa between 2017 and 2019. And these papers, they're all really highly cited, and they played a big role in the results that I showed throughout the early part of this presentation. So now we're moved into the second phase of tour, which is lasting from 2020 until 2024. And we're basically repeating what we did with tour one, but with all new data and updated analyses. So in the database, we're going to update the database with all available ozone observations worldwide at the surface with data through 2021. We'll have a brand new assessment that will be published next year. And this time around, we're going to conduct impact studies to quantify the impacts of ozone on human health, vegetation, and climate. And then here's our timeline. Tour 2 began in 2020. In 2021, we formed our working groups and had our first workshops and began initial data collection for the database. In 2022, we developed our ideas for manuscripts and continued database development. Here we are in 2023. We're now working on our analyses, and the database is almost finalized. And then in 2024, we'll publish the results as a series of assessment papers. And at the present time, we have a community special issue open for any and all papers that have to do with tropospheric ozone research. This is being hosted by 6 Copernicus journals. So if you want to participate, you can submit your papers to ACP, GMD, AMT, Earth System Science Data, Copernicus's Statistics Journal, or to Biogeosciences. And with that, I'm at the end of my presentation, and I'll be happy to answer any questions. Thank you for your attention.
Thank you very much. Oops, it's echoing. Can you hear me properly?
Yes, I can hear you.
Yeah, because I can hear the echo, sorry.
Okay.
It was really, really great. It was an amazing presentation taking us through the tropospheric trends, and also it's a bit scary when we think about the future. So yeah, it's open for discussions now. Anyone has questions, you can unmute yourself and ask questions. You don't have to type it in the chat.
Hello, am I audible?
Yeah, yes, Veena.
Thank you for the talk. I just wanted to ask, the stratospheric circulation is projected to strengthen in the coming climate changing scenario. So how that will have a part in the tropospheric concentration of ozone? And again, thank you for the talk.
You broke up a little bit there. I think you're asking about the future evolution of tropospheric ozone. I'll go back to
how the stratospheric circulation change will affect that.
Oh, how will circulation changes affect it? Yeah, so that will be mainly at the surface, and that's heat wave related. Let me go back to that figure. I actually have a nice figure in a different presentation. I won't be able to find it at the moment, but I can send it to you later. It's IPCC's projections of increased heat waves in the 21st century. And I can summarize that for you here. Basically, in the tropics and at mid-latitudes in both hemispheres, we see a strong projection of hot days above 35 degrees Celsius. And that indicates an increase in heat waves at the surface. And we expect, with those heat waves, we expect lighter winds. We expect stronger temperature inversions near the surface. We expect less cloud cover. And so that all makes hotter conditions, which increases ozone production levels at the surface, and also traps pollutants near the surface. So, so future circulation changes in terms of ozone, the main impact is stagnation events at the surface. which will then increase surface ozone production.
Thanks, Owen. There's a question from Silvano.
Congratulations, Owen, for this great talk. It was really interesting. My curiosity is, do you think that biogenic emissions, which are expected to increase in the next decade, can have a strong impact, especially on those urban and peri-urban areas where we are aiming to plant millions of trees? Most of them are isoprene emitters. What do you think?
Yes, I mean, in the eastern United States, isoprene is highly prevalent all ozone season. And so in the United States, the reason we've seen big reductions in ozone is due to the reduction of nitrogen oxide emissions. The anthropogenic hydrocarbon emissions haven't been so impactful just because isoprene dominates. So absolutely, wherever we have high levels of biogenic emissions, you have the potential to make ozone. But the good news is if you can reduce nitrogen oxide emissions, their impact is limited. And then looking into the future with more heat wave conditions, they're expected to also be associated with drought conditions that can actually shut down vegetation activity. And so you could potentially see a reduction in isoprene emissions during strong drought events where water is limited. So it's a little bit of a two-sided coin. But if we can focus on reducing NOx emissions, I think we can get on top of the ozone problem at the surface, regardless of biogenic emissions.
Thank you.
You're welcome.
Question from Vikrant.
Hi, Dr. Cooper. It was a very wonderful talk. I have a couple of questions. First, regarding the TOR 1 and TOR 2. I believe that in TOR 1, you have different statistical methods to analyze trend than what we have in TOR 2. So by changing these statistical methods, have you also observed any changes in trend? I mean, the value of slopes. Like earlier, you have Saint-Hill's method while computing the trend. Now, the method is different. So do you see any differences in the trends also?
Okay. In terms of the big picture, the trends don't really change. The reason we went from the centile method to quantile regression is that we get a more accurate uncertainty range on the trend. So the centile method, it was developed, 50, 60 years ago, and it's been widely used in the environmental sciences. There's plenty of papers that use it. But it was designed to ignore outliers. And the centile method actually throws away about 28, 29% of the data in your time series in the extremes. And it only focuses on the central ozone values. And so then it has unrealistically narrow uncertainty range. And so by using the quantile regression method, which is much more modern, and it accounts for autocorrelation, and it doesn't throw away any of the data. We've done some comparisons, and this is, you can find this in the TOR 2 statistics guidance note that's on the TOR 2 webpage, where Kailan Chang, who's our statistician, he's compared trends from the centile method and from quantile regression. The actual trend values themselves are very similar. It's just the uncertainty range that changes. And we're just using a more modern method. So I don't expect the big picture to change going from one method to another.
But Dr. Cooper, when we look at the quantile regression methods, we have slope for different quantiles. But if we talk about the Saint-Hill's method, it does give trend, but the value of slope, but only for the mean values. So when we are also comparing, comparing two different trends, then how it is statistically significant while comparing these two, because the ranges from 5th percentile to 95th percentile, the value of trend changes. So it has quite a range.
Yes.
From smaller to higher percentile. But if we try to compare it with the Snell-Hill's method, the value, we just have one single value for the trend. So, I mean, how it is significant while comparing these two. And one more thing, in addition to that, how does the p-value, which tells about the statistical significance of the method, I mean, the linear trend which we are looking for, I mean, how much it holds the power while we quoting it after the analysis of the trend?
Yeah, so the centile method, you know, it gives you the median trend from the whole distribution, but you can still apply that to the higher extremes. You can still look at the highest 10th percentile of ozone, and you can use centile for that. You can look at the lowest 10th percentile for ozone and use it for that. So you can change it for the percentile that you're looking at. The nice thing about quantile regression, it just gives you all these percentiles immediately. It's just how it's designed. And definitely we see big differences in trends between the lowest percentiles, the median,
Exactly.
and the upper percentiles. But that's just how ozone is. Ozone is complicated, and the trends are very different depending on the percentile you look at. And so by using quantile regression and looking at the full range of trends across the distribution, then it's just a lot more informative. So I wouldn't worry about differences between, you know, the centile method and quantile regression. My recommendation is just go with quantile regression. It gives you the big picture view of trends across the full ozone distribution. And then in terms of the p-value, p-value it's useful, but it should not be overly relied upon. You know, in the past, we've talked about trends that are significant and insignificant based on the p-value. And for many, many years, that key p-value was 0.05. Well, there were some very influential papers that were published in the Journal of the American Statistician about 4 years ago now, by some top statisticians that said, you know, we really shouldn't be using this term statistically significant because it doesn't really mean a lot. And we found that with TOR. We would find that trends in a region, you know, maybe some sites had p-values of like 0.01 or 0.02, and they were going down at a certain rate. And then stations nearby had similar trends, but their p-values were like 0.07, 0.15. You know, based on the earlier interpretation of p-values, we would have said that a lot of those trends were insignificant or not meaningful. But we now know that they might not be as certain, they might not be as robust, but we shouldn't ignore them. And so now the method for TOR is to report all trends with their uncertainty range and report all p-values. We don't use the expression statistically significant, but we just look at the data collectively as experts, and we make up our own mind as to whether or not we have confidence in these trends. And we explain that in our papers. So you don't have to use that expression. And it's a new way of looking at data, and I'm excited about it.
Dr. Cooper, one last question. I won't take too much time. So talking about the p-values and significant and non-significant. So if we try to shift from monthly means to daily means value, the number of data points, it increases very much. So, and when the data points increases, then reaching towards the lower p-value, I mean, it's more probable to move towards a lower p-value. So, I mean, is it a good idea to move from monthly means to daily means if we are not getting a good p-value, or it is, I mean, it's a good exercise, but it doesn't contribute to any science? I mean, how do you see it?
Exactly. I mean, right here, you've identified one of the problems with the p-value. It all depends on the quality of your data, the sample size, and how you're interpreting the data. So, in TOR, we've mainly worked with monthly means, but you can use daily data if you want to. And if you want to compare trends based on monthly means to daily means and talk about the difference in the p-value, that's totally fine. But you would just say in your explanation, we see a change in the p-value because of the sample size.
Yes.
So I wouldn't say that one method's right and one's wrong, so long as we all just talk about what we're really looking at and present a range of information. And then you can kind of leave it up to the audience to really make up their own mind as to whether or not they believe the trends or not.
Okay, doctor. Thank you.
You're welcome.
There was a question from Saurabh. Saurabh.
Thanks, Dr. Owen, for a very interesting and elaborative talk. I'm having a couple of questions. One is related to data analysis. Actually, I'm just wondering that sometime when we collect the data from ground-based measurement and sometimes we collect the data from satellite, so we observe there is a difference in the level of the different gases or maybe particulate matter. So during data analysis or interpretation, what are the things that we must consider? That is my first question. And my second question is actually related to ozone only. I'm a bit curious just to know the difference in the contribution of the ozone from that is coming from land-based transport or from shipping related industries in maybe in the South Asia, Middle East, or in US and Europe. So any thought you have?
Yeah. Thanks, Sarah. In terms of satellite data, yeah, I've seen quite a few studies like for India where satellite data have been used to look at ozone trends, because in the past, the surface monitoring has been limited, although now you've got quite a lot of monitoring across India. The problem with the satellite data is most of these satellite, in fact, all of these satellite products have very limited sensitivity at the surface. So most of the signal that you're seeing from a satellite is from the free troposphere. And as I pointed out in my presentation here, trends at the surface can be very, very different from trends in the free troposphere. So yes. If you're trying to understand surface trends, do not use the satellite data, because they don't really tell you what's going on at the surface. They're good for the big picture, for the global scale, regional scale. But again, they only really tell you what's going on in the free troposphere. So you got to keep your surface data separate from the satellite data. And then in terms of shipping, yeah, it's a huge source of nitrogen oxides in the remote atmosphere. And in Southeast Asia, coming through Singapore, and then heading off towards Sri Lanka and India, there's a well-known track of nitrogen dioxide that we can see in the satellites there. And it's a huge source of ozone precursors. And we're making ozone now in the remote troposphere, marine boundary layer, where we never had emissions before, 50, 60 years ago. And what we found from the IAGAS data is that throughout much of the troposphere, especially over Southeast Asia, it's hard to find very low ozone values anymore. It used to be back in the 1990s, whenever they made measurements in the remote atmosphere of the tropical Pacific and Southeast Asia, you could find ozone values quite frequently of 5 to 10 parts per billion. But it's hard to find those values anymore. And there just seems to be a lot more precursors now available in the remote atmosphere of Southeast Asia. Some of that, or a lot of that, could just be due to biomass burning and aircraft emissions and just general increase of the population. But surely the increase in shipping must be a large contributor to that. And I'd love to see some updated studies on the contribution of shipping NOx to ozone levels in the remote atmosphere of Southeast Asia and South Asia.
Okay,
I hope that answers your questions.
Thank you, Owen.
Yeah.
This question from Sharfa.
Hi, Dr. Cooper. Thank you so much for your very informative talk. My question is rather, I would just like to know your take on it. Like you said that aircraft emissions have been increasing recently, and especially for India. Like the policies that India has are already substandard, and our efforts in cutting down emissions are regarded as highly insufficient. So is there a way we can compensate it? Like, what would you advise for India? That is my question.
Okay, well, in terms of aircraft emissions, there aren't really any policies that can reduce nitrogen oxide emissions from aircraft. Aircraft already are a highly efficient, machines in terms of transporting people. They operate at very high temperature. And at these high temperatures, you're just going to produce nitrogen oxides. There's no way to escape it. It's not like automobiles where you can fit catalytic converters and reduce nitrogen oxide emissions. So as aircraft traffic increases and as more and more jet fuel is burned, we're going to see a proportional increase in nitrogen oxide emissions. And that doesn't matter if you're in India or the EU or the United States. So there's not much that can be done in terms of reducing nitrogen oxide emissions from aircraft. I mean, they are making aircraft more efficient. They're lighter now. They get more meters per kilometer, or more meters per liter, I guess, if you can even measure it in that sense. But you're always going to have a lot of nitrogen oxides. And then in terms of how India can best control its surface ozone pollution moving forward, especially with the challenge of climate change, the focus has to be on reducing surface nitrogen oxides. And that's got to be getting away from fossil fuel combustion, and it's got to be getting away from crop burning, which I know is probably not practical for India. I mean, you have a large population and you need to produce a lot of food, and to clear the fields twice a year, the common practice is burning the crop residuals. And, the only way to get past that then is mechanized farming, which unfortunately produces more emissions. So if India can move forward with more renewables and reducing fossil fuel combustion, that's probably going to be the most effective way to reduce surface ozone pollution.
Okay, thank you. Thank you so much.
You're welcome.
Thank you, Owen. So I don't see any other questions. Pallavi, if you don't have any questions, maybe you can summarize and.
Thank you very much, Owen, for such a terrific talk. I really enjoyed the talk and also the discussion.